Section 7.5, a general factoring strategy, which is a nice way of saying we're about to mix them all together. So it's a mix of all problems, which means finally being boringly good is about to pay off, because it's going to be critical that we ask these, because there's going to be all kinds of different sizes that we're looking at. Always checking for the GCF, and then is it 2 terms? Well, that means we do this. Is it 3 terms? Well, that means we do this. Is it 4 terms? Well, that means we do this. This is going to be your roadmap, so to speak, of how you can navigate these different types of factoring problems. Well, what would that look like? Once again, let's review. This is good to always review. It gets it into long-term memory, but for those of you who are kind of picking and choosing which videos to watch, hopefully at least one you'll catch the big picture here of what we're doing. The steps, what we're trying to do when we're factoring, and then some information that'll help you, pardon me, and then a little bit of information that'll help you if you're converting 3 to 4 terms, which is what the majority of the factoring will be, is when you're dealing with the trinomials. So let's do a little bit of review here. Our first step, which we learned in 7.1a, is to check for the GCF, always. We want to check for that first, always. Okay, always look for a GCF. Is there something that all the terms, no matter how many there are, but is there something all the terms have in common? The next thing we ask ourselves is, how many terms are we looking at? Whether we pull a GCF out or not, what's left over is what we're still trying to factor. So in 7.4 most, the beginning of that part of the section, we looked at what do we do if there's just 2 terms. Well, there's some special formulas that you would apply if you're looking at a difference of squares, or a difference of cubes, or a sum of cubes. If you're looking at anything else, including a sum of squares, there's no formula, that's not factorable. So you have to be looking at one of these, difference of squares, difference of cubes, sum of cubes, and then you apply those formulas. And those are all in 7.4 most. If you're looking at 4 terms, skipping down the list a little bit, from 7.1b, the second part of 7.1, with 4 terms, you go straight to factoring by grouping. And the reason we skipped over 3 terms is because then our method for 3 terms, which we covered in 7.2 and 7.3, was to go ahead and convert back to 4 terms so that we could use the factoring by grouping. Most people find that factoring by grouping, once you get the hang of it, really easy, not very time consuming, able to catch the negatives. It doesn't cause a lot of issues for people. So it becomes a nice option. Now, there's other options for 3 terms as well. Trial and error. There's the box method. Either of those I'm happy to go over in class. Just ask me and I can show you some different options. But with, and actually the box method is just a visual format for placing the converting to 4 terms. It's just another way to look at factoring by grouping. So it's really nothing new. But then just most recently we added in, using the leftovers of 7.4, we looked at how you could do 3 terms if it were a perfect square trinomial. So we'll just add that to the list now. The 7.4 leftovers had 3 terms, a special formula for if it's a perfect square trinomial. Oh, having trouble spelling trinomial. And I did it twice. Wow. Trinomial. Okay. So what is factoring? Well, factoring is just basically we're splitting apart the multiplication or the distribution or the foiling that has already happened. So it's almost like we're working backwards through the problems. We learned how to go forwards through them in Chapter 6, where we learned how to FOIL and distribute and multiply. But now we're splitting them back out to factor. And some of you might go, why are we doing this? Why do we learn one direction and then we learn undoing it? Well, same concept. You learn how to add and then you learn how to subtract. Well, subtraction is undoing the addition. You learn how to multiply and then you learn how to divide. Division is undoing the multiplication. We're just undoing some multiplication here in algebra to get the factors. Well, why would we do that? Hang in there. In 7.6, our very next section, we'll look at how this this technique of being able to factor will help us solve equations. Notice we haven't seen an equal sign in many, many pages of homework. And that's because we're just trying to factor, just trying to split things apart. We're going to add in an equal sign and be able to solve now for some very important pieces of information. We'll get to that in 7.6. I don't want to give it all away now. Okay, and so if you decide to take the 3 terms and split it into 4, let's recall that the goal of splitting 3 terms to 4 terms is a strategic split of the B term, where you're trying to really get it back to its original outside and inside pieces that you got when you FOILed. They ended up usually being like terms, this outside, inside, this OI piece, and they would then combine. And so your 4 terms that you got from first, outside, inside, last became 3 terms. So our goal is then to go backwards from 3 to 4 and split that back up into its original O and I's. Outside, outside, inside, inside. And then you can factor from there using factoring by grouping. The standard form of a trinomial, the pieces of information we need, come from the fact that you see ax squared plus bx plus c, and then we're able to use the a, the b, and the c values to get to where we need to go. So that's our little bit of review, and now the being boringly good pays off because they're all going to be mixed together. The instructions say factor completely, which means you need to keep going. You need to keep checking, are we done, are we done? Or state that the polynomial is prime, and we can always check using multiplication. Anytime you get to the bottom, and I have not been a good example of that, remultiplying it back out to check that we got back to the original. But if you're ever unsure at any point, you can just refoil, redistribute, multiply it out. Many of you could do this in your head at this point to make sure you could get back to the original. If you can, then you're on the right track for factoring. Okay? So let's look at number 14, 2x to the 5th plus 128x squared. And before you start trying to decide anything, you want to ask yourself, being boringly good, does this have a GCF? Is there something that both of these have in common? In fact, yes. Not only do they have a 2 in common, 2 can go into 2 and it can go into 128, but they have an x squared in both. So we're going to pull out a 2x squared as our GCF. And what that leaves behind is 2x to the 5th divided by 2x squared. You should leave behind the x cubed. And you could always check that by redistributing it. 2x squared times x cubed is 2x to the 5th. It also leaves behind a plus. You just bring that sign down here. 128 divided by 2 is going to be 64. And x squared divided by x squared leaves you x to the 0, or just plain 1. So what's left behind is x cubed plus 4. And so our next question is, being boringly good at this factoring stuff, how many terms are we looking at? And we're talking about the leftovers here, not the GCF. In fact, I'm going to go ahead and scoot that GCF down to where my answer will be so that I don't leave it out. It is a factor. It's the greatest common factor, but it is, when it says factor completely, we need to show all the factors, including the GCF. But how many terms are left over? Well, there's 2, which means that we're in the special formulas situation. There's only 3 options here. It has to match either a difference of squares, a difference of cubes, or a sum of cubes. Anything other than those 3 situations, and it does not factor. We would be done at this point. Even if it looks like a sum of squares, it feels like, oh, maybe that should have a way to factor too. There's no way to factor out sum of squares and still get back to what the original was. So do we have difference of squares, difference of cubes, or sum of cubes? Well, it's plus, so we know that it's not either of the differences. So is it a sum of cubes? Well, x cubed is a cubed, x times x itself multiplied 3 times, that is a cube. And 64 is actually a cube as well. 64 is that number that we talked about in one of the earlier lessons. It's both a perfect square and a perfect cube. As a cube, it's 4 times 4 times 4. So we have a sum of cubes situation, which means that you're going to have to recall from memory the formula you'd want to use for this. How are you going to get that memorized? Well, my suggestion is every time you use it in these homework problems, you write it out as well as say it as you're writing it, so that you say it, see it, hear it, and say it, see it, hear it, and you're writing it out at the same time. So that you're memorizing 4 times as fast. So what is the formula? Well, formula for a sum of cubes is if you have a cubed plus b cubed, that factors into a small term and a big term, 2 terms and 3 terms. The first one is your a and your b. The long term is a squared at the front, b squared at the back, and then you multiply the a and b together for your middle term. Okay, not doubled, just plain old ab multiplied together. And then the signs, what do you put for the signs? Well, it always follows the SOAP pattern. So it's the same as what you started with. That's the S in SOAP. It's the same, so it's plus. It's opposite of what you started with. The opposite of plus is minus. And then it's always plus. Always plus right here. Always positive. So in this case, for a cubed plus b cubed, it's a plus b, a squared minus ab plus b squared. And now I fill in the pieces, where x is my a value, 4 is my b value. So my factored version of the x cubed plus 64, and that's what we're factoring right now is x cubed plus 64, is my a and b, x and 4, a squared and b squared, x squared, 4 squared is 16. My ab multiplied together, that's 4x. And then I do my same opposite, always plus. We have a plus, so I go same as plus, opposite of plus, and then it's always plus. There's always a positive in that third spot. And that is the factored form. I don't have to try to go any further. Once I've factored a difference of cubes or a sum of cubes, it's done. Okay? So here's our final version. Good thing I'd written it down because I'd forgotten already that I had a GCF going on. There was so much else happening. So I have my GCF as my first factor, and then I have my x plus 4, and then I have my x squared minus 4x plus 16. And you could put the GCF in parentheses as well if you prefer. If you don't, that's fine too. And these can happen in any order as long as you have one that looks like x plus 4 and one that looks like x squared minus 4x plus 16. And one that looks like 2x squared. Multiplication is commutative, so any of the order does not matter here, just inside each parenthesis should look like that. Okay, and now let's try for number 54. We start with asking ourselves, does it have a GCF? Yes, it does. Oh, and I just realized I did not pull down the video. That is such a bummer. So I'm going to pause it right here, restart the video, and do the next problem again. Sorry.